Next speaker is Trevor Lanting from D-Wave, who will tell us about the latest and greatest 2000 Q chip. And Trevor, it's all yours.
Great. Thank you very much. My name is Trevor Lanting. I'm a scientist at D-Wave Systems. I work on the team developing our quantum annealing processor technology. We've been working on developing a series of practical tunable quantum annealing processors over the last few years, and I want to spend a few minutes today telling you about our latest generation of processor, what we're calling the D-Wave 2000 qubit processor. So I'll do a brief introduction of the processor itself. I think a lot of people are familiar with the basic idea of quantum annealing processors. I'm going to talk a little bit about some initial optimization data on a synthetic benchmark class we call the frustrated cluster loop class. And I want to spend the bulk of the talk on some things that we're very excited about with this new generation of processor. So we're expanding the tunability, or the control that users and researchers have over the annealing process. All the processors to date have implemented something we term just the standard quantum annealing protocol. And we've generalized this to allow for sort of static per qubit flux offsets, or per qubit anneal offsets, so we can programmatically delay or advance the annealing process on a per qubit basis. And we're allowing users to change the global schedule. So instead of just the scaling of anneal time from sort of microsecond scale to millisecond scale, users can start changing this global trajectory, adding an anneal pause and anneal quench midway through the annealing process. And I'll go into this in a lot more detail. So here's a picture of the processor itself. So we fabricate our processors on 8-inch silicon wafers, and we dice out each one of the processor die. They're about a centimeter square. So this shows a picture of one of our 2000Q processors bonded up to a printed circuit board, and this entire assembly gets mounted to the mixing chamber of a dilution refrigerator. Typically, we've been operating our processors at about 12 millikelvin. It's a 16 by 16 grid of 8 qubit unit cells. So each one of the 8 qubit unit cells is a K44 grid. So a bipartite graph with 4 horizontal and 4 vertical qubits with 16 couplers that you can in situ tune. The basic building block is an RF squid flux qubit. The on-chip control and the external biases allow us to treat this like a spin 1/2 particle or a tunable quantumizing spin. We can in situ program spin glass Hamiltonian instances, so we can actually tunably turn on and off couplers and local fields on each one of the qubits in the processor. And we can scale the quantum annealing algorithm time, the time in which we run this quantum annealing process, from microsecond scales out to millisecond scales. So this Hamiltonian should be familiar to a lot of you. There's 2 important energy scales. So there's A of S and B of S. This entire thing is the quantumizing spin Hamiltonian. And annealing is run first by starting with A of S completely dominant, so the transverse energy dominates over every other energy scale in the system. So the processor starts out in a global superposition of all possible computational states. As annealing progresses, A shrinks and B grows, and B is a prefactor in front of the actual icing Hamiltonian. And we're interested in ground state or low energy configuration, second term, so the second half of the Hamiltonian. This plot here shows typical energy scales. S here is just a normalized anneal fraction. Normally, we choose a global trajectory that grows B of S, this problem Hamiltonian scale, quadratically in time. One thing to note about the flux qubit design currently is that a single time-dependent bias, single global bias, simultaneously changes A and B. We don't have orthogonal control over 2 halves of the Hamiltonian. So both A and B come along for the ride when we have this global time-dependent signal that actually effectuates the annealing algorithm. So here's some initial data that we took on the 2000 qubit instances, and we're focusing on the frustrated cluster loop problems. So a lot of this work was written up by one of my colleagues, Jamie King. You can find a link to the work here. But this synthetic benchmark class combines the local complexity of the Google cluster problems that have been developed, along with the global complexity of frustrated loops, planted solutions of frustrated loops. So the idea behind this problem class is that every unit cell, we bind all of the 8 couplers, or the 8 qubits in a unit cell tightly together, so they're forming an effective 2-level system. So they're tunneling into the all up state and the all down state. And then on that logical graph, we lay down these frustrated cluster loops. And that combination gives us ruggedness tunability. So we can actually tune how tightly we couple these clusters And we can also tune this precision requirement. So we can make sure that the precision requirement on the pressure loops doesn't grow with problem size. So this is a typical example. These are typical data at a few of these precision row values from row equals 3 to 6. What I'm plotting is as a function of logical qubit size. So this is the size of the working graph, or the size of the number of unit cells, 4x4 grid, all the way up to the whole 2,000 qubit grid. And this shows the time to solution of the 2,000 qubit hardware. So this is the 2,000 qubit D-Wave hardware shown against some classical solvers. So you can see that the time to solution grows as the logical lattice size grows from the C4, the 4x4 grid, to the 16x16 grid. But we're performing quite well as compared to simulated annealing. So this is simulated annealing run on a single GPU, as well as two other solvers. Spin vector Monte Carlo, which is a classical heuristic that scales fairly well on some of these problems, and then quantum Monte Carlo. We're also showing the scaling of HFS. So this is the tree width aware solver run on a single CPU. So if we just look at the C16 scale, so the 16x16 grid, so this is the full 2,000 qubit problem set, we can tune this ruggedness, so we tune how tightly we couple these clusters together, and we can study the performance of the D-Wave hardware as a function of this ruggedness parameter and compare it to some of the software solvers. So in particular, as we tune the ruggedness, we see that the problems get harder. So this is tuning the strength and with which we're coupling these unit cells together. But the scaling of the two heuristics, simulated annealing and spin vector Monte Carlo, are actually performing fairly as we increase this ruggedness parameter. Whereas the quantum Monte Carlo run in a CPU and the D-Wave QPU are scaling relatively well. So again, I want to note that we're not quite at the optimum annealing time. We can't actually anneal these problems fast enough to look for the global optimum. But the performance looks promising. And I think later tomorrow, we're going to hear from Neil and his group. He's actually looked at a similar set of synthetic benchmarks. We're able to identify an optimum annealing time. So we're actually pretty excited to hear about that work. Okay, so as I mentioned at the start of the talk, we've been running essentially previous generations of hardware have run the standard quantum annealing algorithm. So a quadratic growth in the problem energy scale with time, and this applies to all of the qubits in the processor. There's a lot of reasons why we might want to modify this algorithm, when we might want to actually change this and give users and researchers more flexibility over this process. For example, there's a lot of work theoretically that show that if you're running into instances that have, say, a large amount of degeneracy or have first-order phase transition, that there may be an advantage in changing your path and doing something on a per-qubit basis. There's a small number of global time-dependent controls that actually go from room temperature and actually implement the quantum annealing algorithm. And so this puts some constraints on how generally we can modify this annealing path. In particular, we're focusing on two techniques for the D-Wave 2000Q system: a per-qubit static advancement or delay. So on a per-qubit programmatic basis, you can decide to advance or delay qubits. And then a global change in the trajectory. So instead of just this quadratic growth in B of S over time, we can insert changes in this, and we can actually decide to pause or to ramp or to just generalize, taking from S equals 0 to S equals 1. So for the per-qubit control, what we've added is a per-qubit static anneal offset. So all of the qubits are still seeing this time-dependent signal that grows the problem Hamiltonian quadratically in time, but we can actually delay or advance with a local static signal that's provided by a local on-chip control. So shown here is the A and B. So to illustrate this, I'm showing A and B here for the baseline. So the unoffset devices in blue. So in this case, if I add an advancement, so I change the static bias, so I by something like 2% of the total annealing trajectory, what I get is the green curve right here. So again, like I mentioned, both A and B simultaneously get tuned with this annealing signal. So both A decreases and B increases for the green curve with respect to the baseline. And I can flip the sign of this annealing offset, and I can actually delay the annealing process for another device. And what I'm showing here is the energy functions for a delay, where you can see relative to their neighbors, a qubit that has been delayed has a larger A of S and a smaller B of S. So again, both A and S A and B are affected by the static offset, but this allows you, on an individual basis, to decide whether to advance or delay devices. So typically with current hardware, we can offsets about roughly 10%. So in this case, for our processors, about 12.5% of the total annealing path from this annealing bias from 0 to 1. So this gives us quite a bit of dynamic range and control for this delay knob. So where would we want to be able to use this? Well, to illustrate the efficacy of advancing and delaying, we expect that instances that, like I said, have a large degeneracy in excited states to respond to changing your anneal path on a per qubit basis. So how do we actually determine a modified anneal path? Well, we can use an algorithmic approach similar to one already proposed by some colleagues about 5 years ago. And actually, there's been a lot of other work, I think there's a lot of work by Altshuler and Fari on actually how changing your path on a pre-qubit basis to actually avoid a first-order phase transition or to lift a small gap in an instance. We actually used a 24Q test bed of 100 instances, and we mined this from a much larger set of instances so that these 100 instances have large excited state degeneracy in a single ground state. I'm not going to talk too much about the construction of these instances or the mitigation algorithm itself, but I want to point you to a talk by my colleague Andrew King tomorrow. He's going to go into this in a lot of detail. But the basic idea is that you begin by annealing all the devices the naive way, so you don't apply any per qubit offset, and you collect some number of samples, and you do a calculation on the samples to decide on a per qubit basis whether you want to delay or advance or some degree between those two. So you can apply this algorithm several times. So this shows the behavior of the processor on the set of 124 qubit instances after a single iteration of this algorithm and after 4 iterations of the algorithm, where I'm plotting the probability of seeing a ground state configuration scattered against a single iteration of this instance, or this algorithm, and 4 iterations of this algorithm. You can see that there's an improvement across the vast majority of all these instances. And after the 4th iteration, we've essentially boosted our probability of seeing a ground state to something close to unity. So this gives us a lot of confidence that this would be a very powerful tool for at least these testbed 24-qubit instances. We've actually have some evidence that it's helping across a broader range of instances as well. So we're actually excited about this, and we think that this early algorithmic mitigation technique actually could apply more broadly to a lot of other instances. So the second direction, the second generalization that we're giving users and researchers with the 2000Q product is, the processor is changing your global annealing trajectory. So there's a global time signal that actually grows the problem Hamiltonian and shrinks the transverse field. And traditionally, we've just grown the problem Hamiltonian scale quadratically with time. So an example of a generalization to this is you could interrupt that growth midway through the anneal, for example, halfway through the anneal, and then sort of pause at a particular point. In this case, I'm comparing a 20 microsecond anneal with the standard growth of the problem Hamiltonian with the insertion of a 100 microsecond pause midway through the anneal at s equals 0.5. So why would we want to do this? What good might this do? Well, instances that have perturbative crossing, so instances that are going through a minimum gap, may respond very well to the insertion of a pause at the point where you're hitting that minimum gap. This allows you to identify regions during the annealing process where dynamics are occurring. So it's a nice diagnostic probe of freeze-out or localization, so where dynamics are actually occurring in these instances. And as we understand sampling, and as we try to understand the equilibration behavior of our quantum annealing processors, the insertion of a pause midway through the anneal may actually allow us to better get at an equilibrium, or better achieve an equilibrium distribution midway through the annealing process. So here's some example data on a 16-qubit instance. We actually published some other data on this instance about 4 years ago. So this instance here has a 256-fold degenerate first excited state and a single ground state. With the current annealing schedule, the current A of S and B of S, this instance has a minimum gap at about 0.325, at S equals 0.325. And that minimum gap is on the order of a microkelvin. So it's very small compared to any other energy scale in the system. What I'm showing here is the application of one of these anneal with pause calls. What I'm showing with the 3 different colors are 3 different background anneal times. So 10 microseconds, 100 microseconds, and 1,000 microseconds. And then we're introducing this pause at different points in the annealing process from s equals 0.1 to s equals 0.6. So this, the x-axis indicates the anneal fraction, or the position in the annealing process where we're inserting the pause. And then there's 3 different data sets in one of the colors, which represent pause times of 100, 10, 100, and 1,000 microseconds. So there's a couple things to note. First, this instance is very sensitive to the background anneal time. So we can change the probability of seeing a ground state configuration by over an order of magnitude by changing the background anneal times from 10 microseconds out to a millisecond timescale. The second thing to note is that inserting the pause very early in the annealing process or very late in the annealing process has no effect on the spin statistics coming out of the chip. This is to be expected. So pauses that are inserted very early where dynamics are very, very fast, these dynamics are very fast compared to that pause timescale. So there should be no effect of the presence or absence of that pause. Later in the annealing process, after s of 0.5, dynamics have essentially ceased. So the spin statistics, or the distribution, has frozen in at this point, and the presence or absence of the pause has no effect on the statistics. But you can see that midway through the annealing process, in the vicinity where dynamics are starting to slow down, there's a dramatic effect on the success rate, on the probability of seeing a ground state. In particular, at around the vicinity of the avoided crossing, you see the ground state success rate spike up significantly. And in particular, for the longest pauses, so the 1 millisecond or the 1,000 microsecond pauses, you can see that the statistics have essentially decoupled from the background annealing time. So we think this is early evidence of us actually getting at equilibrium distributions at this point. So that the approach into and the exit out of the pause do not change the spin statistics. It's the presence of the pause itself that's dominant. Another modification to this global trajectory that we've been studying is a mid-anneal quench. So in this case, you can interrupt the annealing process with a very fast ramp. So you anneal slowly, some intermediate value of s, and then you pull the barriers on the qubits up quickly, so you of s and increase b of s quickly. So why would we want to do this? Well, you'll hear from my colleague Jack Raymond on Wednesday that this may help us actually achieve quantum Boltzmann distributions midway through the annealing process. So to get at actual equilibrium distributions midway through the annealing process, you want to anneal slowly to some point s and then quickly terminate the annealing process, or quickly quench or kill the transverse field. The current hardware allows you to quench at 1 microsecond timescales. So we think that as we build up sort of knowledge about how the hardware is sampling and knowledge about how we're actually producing quantum Boltzmann distributions, this could be a key enabling technology for example, machine learning. So in summary, the few thousand qubit scale processor start studying very interesting problem classes. So this frustrated cluster loop class looks like it's a good test bed for really understanding the computational role of tunneling. We're excited to hear about some of the work that Dan and his group have done on a similar set of problem class. The increased control of the annealing process, in some cases for some test problems, has really generated a large boost in performance. And it's been a useful diagnostic tool for really understanding the efficacy of the quantum annealing algorithm. In particular, the per qubit control, you can start linking up with some algorithmic mitigation techniques, some actual feedback algorithms, and we've already seen for these test instances a big boost in performance when we do this. The global manipulation of this anneal schedule is also a key diagnostic tool, and it actually could really improve the sampling performance of quantum annealing systems and actually link up with hybrid sampling algorithms and machine learning very effectively. And then I also want to point you to another talk by my colleague on Tuesday morning. Richard Harris is going to talk about an entirely other set of measurements on the 2,000 qubit processor, where we're looking at sort of cubic lattice problems, and we're looking at running quantum annealing on these problems embedded in the 2000Q hardware. And finally, some of the things where we want to take this technology are a concept that we're calling reverse annealing. And I don't want to get into too much detail because I'm running out of time, but this idea here is that you see the hardware with the classical spin state, and then turn on the transverse field to some point midway through the anneal, and then study the samples that you get when you actually run this protocol. So we think this actually may be important for hybrid sampling algorithms when we're actually linking up with machine learning algorithms. then finally, support for virtual topology. So actually, better support for embedding things like cubic lattices and bipartite by expanding the dynamic range that we can use to couple qubits together is something that we're pushing for this technology. Thank you very much.
Thank you, Trevor. And we have several questions.
This is the comment. We have shown that it is sometimes better to stop the annealing process in the middle of the process with finite transverse field than to reduce it to zero in some cases by some numerical calculations for some systems, and the results will be announced at poster 27 today.
That's right.
To mitigate the effects of noise.
Not to mitigate the effects of noise as much as to understand what we're calling quantum Boltzmann distributions. So, right.
So I just wanted to make sure I understood. On your per qubit control, does that mean that all 2,000 qubits could be individually offset even with different values?
Yes.
Okay.
Yeah, it's a per qubit knob, so you can decide arbitrarily on a per qubit basis to advance or delay by some amount.
Okay. And on the case where you delayed and you saw some improvement in the probability of success, the intuition is that you've probably gone through a small gap and you're in the excited state, now you're waiting, it relaxes back to the ground state, and then you continue on? Is that the idea?
Well, with the per qubit control, and you'll hear more tomorrow, because we've actually done exact diagonalization on these instances with the mitigation biases in place. And we actually see that these instances are going through a minimum gap, and that gap is actually getting lifted with the per qubit change. So you're actually you're not getting stuck in the excited states with as high probability as you are without mitigation.
And then with the delay where you're waiting, you stop the annealing and then you pick it up again?
This one right here. So
yeah.
this is another instance. So the intuition is it's a similar structure to the problem. So it's not the same problem as the 24 qubit instance, but there is a minimum gap. And so by waiting, you're able to give the processor enough time to tunnel into the ground state.
Right. So you've gone beyond the gap and then you relax back.
That's right.
Okay. Thanks.
Masood? Right.
So I have a question on this slide again. So what problem classes did you benchmark this, that you saw this improvement?
So this is in particular just for this 16 qubit problem. So this is a single problem that we studied in depth with.
Oh, so the one that is in the initial communication.
Yeah. So we took that instance. It was a nice example of an instance that was relatively small scale, but had a very small gap.
Okay. So have you tried anything on disorder system when there is like because there is a lot of symmetry in that problem class, as I remember.
Right.
Did you try anything that is like random with disorder and see how it is performing?
So we've studied a few other problem classes where we've inserted pauses and seen changes in the spin statistics. We can maybe talk a little bit more offline. So this problem here is just a nice demonstration of why you would want to insert a pause just as a diagnostic tool. As a computational tool, it's not clear. You need to know exactly where to insert the pause. But for example, if you wanted to improve your equilibrium statistics, or you wanted to try to equilibrate at a particular point, at a particular S value, you might want to combine a pause at a particular location along with a fast quench or a fast ramp out of that point to try to get a better distribution at some intermediate point in the annealing process.
Another question on this. Another technique that you allow for individual spins to be delayed. What was the ratio that you can delay this? Because there's some limitation that I think the last time we discussed this. Is there any progress in the sense of variations in the individual spins to be comparable on the time scale of the annealing itself? So I just want to know what's the time scale that you can delay the maximum.
You mean the per qubit offsets and delays? So right now, it's not practical to do an independent time dependent control on every one of the qubits. So this is a static bias that we're applying to every one of the qubits. and you can tune the sign and the magnitude of that bias. The external bias increases from some value, call it 0 at the start of the anneal to 1 at the end of the anneal. I showed typical values of A of S and B of S for a 2% advance or delay, the static advance or delay. But typically, the maximum we can achieve with the current hardware is just over 10% of that entire annealing bias swing.
Okay. More questions? Seth.
So this is really nice work, and it's a really great exploration of what's happening in the vicinity of the quantum phase transition and the minimum gap. So, I think I find it very interesting that if you stop and wait for a long time at that vicinity to try to equilibrate and then get out, the fact that this seems to work quite well indicates that there's not that many additional states that you're thermalizing with at the vicinity of the gap. So, okay, a question, am I right about this? Do you know how many there are? Do you know what's more about what's going on right there?
So at least for this problem in particular, the gap between this first excited state manifold of this 256-fold degenerate state and then the second set of excited states is fairly large, and we're just not seeing any of those states when we insert a pause midway through the anneal. So, but in general, I think it could be that long pauses allow you to actually start exploring some of the you might actually see some of the other states as well.
I see. So your gap is your gap bigger than the temperature then at this point?
So this gap right here is much smaller than the temperature. So the gap between the ground state and the first excited state at the voided crossing is on the order of several microkelvin compared to millikelvin scales.
But the gap between the first manifold of a whole bunch of states is large. Is that what you were saying?
Between that first manifold and the next manifold is very large compared to temperature.
Yes.
Yeah.
Right. Okay. Good. I understand.
Yeah, but at least for this instance. But this instance has been specially crafted. So.
Yeah. Can I ask something? I mean, if you were completely 100% adiabatic, so you were in the ground state.
Could you use the microphone, Eddie?
Yeah, I don't know. Is it on? Yeah. So if you were completely adiabatic and you were in the instantaneous ground state and you paused, I would guess that very little would happen because you would just change the phase and nothing should be occurring.
Right.
But so it seems like if you're getting an effect, it must be because of you're really in a thermal state. Is that right?
I think you're in the thermal state, and you're also able to evolve non-adiabatically for this instance. So you're able to go through. So even if you were able to actually run this instance at a lower and lower temperature, I think you would see a low probability of seeing a ground state configuration because you are seeing this avoided crossing between the ground state and the first excited state.
Yeah. So speaking of low probabilities, I can't really read it too well, but at the bottom is that 10 to the minus 4?
This is 10 to the minus 4.
Okay, so those are 10 to the minus 3 at 16 qubits. So these are very low success probabilities on this instance, right?
Right, yes.
Okay, so you're starting with a very low success probability, and then you're jacking it up a little bit.
Yeah, in some cases jacking it up to close to a part in 10.
Oh, that's much bigger. Okay.
Yeah.
By 3 orders of magnitude.
No, it's a lot. You're a lot. But why did it start so low? I guess that's my question. Why is it so low to begin with?
I think in large part because the gap between this 256-fold degenerate excited state and the ground state is less than 10 microkelvin. And so on these timescales over which we're actually annealing, I think that you are evolving highly non-adiabatically. Yes.
So you do much better if you leave the ground state
Yeah.
and then you relax back down to it.
Relax down. Okay.
No, it's a very good question. Yeah. So,
Thank you for saying it was a good question.
you're welcome.
All right, to all our intimate listeners, there are some private discussions going on here, but I think that's a sign that it's time to break for lunch, so thanks everyone.